Good afternoon, Precalculus. And today we are going to be working with what does 1 to the infinity equal? And we're going to determine how the number e has come about. So what we're going to be working on today are problems 62 through 65 and 67 are what I'm expecting for homework, and I'll go through briefly of 62 to sort of show what exactly is going on. So in 62 we have our limit as limit of, ooh, that was a mistake, not the previous work. Alright, so we had the limit, I'll actually go thinner, limit as n approaches infinity of 1 plus 1 over n to the n. Now, when we first look at this, in A, we have what happens to the expression inside the parenthesis. So in A, we're looking at just sort of this part. So we're ignoring the exponent for the meantime, and if we think about it, we end up with 1 plus 1 over n as sort of our thing. And if we look at it, this term, because it's 1 divided by a really big number, would end up going to 0, so we're just left with 1. So what we could expect, just by looking on the stuff in the parentheses, that we end up having 1 here, so we'd say 1 for A. However, because we have this exponent that's increasing, normally with any other possible exponential function that's increasing, we end up having a limit that is infinity. So we think it could be infinity because, 1, this is bigger than 1 in here, and that this gets bigger and bigger and bigger. And so when we do this, we'll actually notice we have quite a battle on our hands, and so for C, we'd plug in this function for larger and larger values of n, and we end up getting a number that is closer and closer to what is called e. And so to do this, I've made a little Desmos thing. So I've made this little slider on Desmos, which can sort of let us take a look and sort of try it for between values of 1 to 1000. So we can increase our values. So if we go to 10, we end up with 2.59. We go a little higher, 30. We end up with 2.67. Keep going, 2.68. Going, 2.69. Nice steps of 10. 80. We keep going and going and going, and it doesn't look like it ends up going towards 1 or infinity as we keep increasing this value. It seems to hold itself at a pretty steady number, which we can even increase this to say 100,000. We keep going and going and going and going. And we go to even more. Let's max it out. And as we get there, it crashes. It crashes hardcore. Yeah. So we end up with something about 2.71. And if you actually calculate out the value of what is called e, it's 2.71828, 182846. And, at about 10,000 digits, we're actually getting pretty close to a value of 10,000. We actually get pretty close to this number. Now, where this number ends up coming into play has a lot to do with what is called exponential growth, which you have learned about sort of doing exponential equations, but the idea here is that this is now the idea of when we do compounding interest, we have ideas of we have annual compound interest, we have monthly. In this case, E is representing the idea that we're compounding continuously. So every single moment, we're adding interest to our principal. So you're going to sort of investigate this first by sort of seeing what happens when you have an equation. We're looking at two different forms of our equation here. So we're going to have 1 plus 3 over n to the nth. And we're curious as to whether or not in 64 this will turn out to be 3e or e to the third or something else completely. So we can actually go back to our little Desmos. And we can change our function. And so let's go ahead and put a 3 up here. And let's see if it's 3 times that. Nope. Let's see if it's e to the third. And yeah, it looks pretty close to e to the third at our sort of approximation over here. So we could safely say for 8-64 that the limit would be e to the 3, so e to the third rather than 3e. And I think we can probably assume the same thing is going to happen over here, that it's going to be e to the 0.2 rather than e to 0.2e. So let's go ahead and try that. And just to make sure. And what do you know? E to the 0.2, 1.22. So we're overall doing pretty good here in sort of determining how this function works, where the sort of value in here determines part of the exponent similar to this. So when we go to 8-65, we have these couple of different types of interest plans, and basically what we can do is we can use this sort of general function we've written to sort of demonstrate these various types of interest, where if we have in A, we have it compounded quarterly. What we would do is, since we have it compounded quarterly, what we would do is we would write it as such. So it's 6%, so it would be 1 plus, and we do 0.6, or 0.6 I should say, over n, which is the number of times it's compounded each year. So since it's compounded quarterly, it's compounded 4 times each year, and then we'd raise it to the 4th, and that would be how much, that would be our rate of change each year, how much it grows. And then, so this would be our rate, and then we'd multiply it by our 1,000. So we have 1,000 times this. And then when we solve it out, we should get a value of, let me see here. Let's do 0.6. Let's set n at 4. And then let's do, and then we multiply it by 1,000, we would end up with about 1,061.36. And then we can do it again for our next one, where we're in Bank 2, we're going to be looking at 6% annual interest compounded monthly. So we set it up very much the same, so it'd be 1,000 times 1 plus, it's still a 0.6 interest, so 0.06 divided by, however, instead of it being, since it's monthly, instead of it being compounded 4 times a year, it's going to be compounded 12 times a year. And we're going to raise that to the 12th because that's how many times it's compounded. So we do all that, and we end up with So when we do that, we actually end up with slightly more money. We have 1,061.67. So just by sort of compounding at a faster, like more amount of rate, we end up having a little bit higher amount of money. So now in C, we're going to go even bigger. So instead of being monthly, we're now doing it daily. So if you can guess, it's going to be 1 plus 365, or nope, boop, mistake was made. 1 plus 0.06 divided by 365 raised to the 365. And let's just see how much difference that actually makes this time around. So we'll replace n with 365. And when we do, we now make slightly more money still. 1,0, that was a bad 0. 1061.83. So just by compounding continuous, like more often, we end up with slightly more wealth in our pockets. And then I will let you all sort of do part D, which will be an hourly compounding interest, which might make even slightly more of a difference comparatively. So these are the ideas that we're sort of playing with here. And I'll let you all sort of finish 65 and continue on to 67 to sort of understand all this. And as always, I'm available for questions or to go through with this further. Yeah, good luck to y'all.